Welcome to the Things of the Stars, Sleeping with Science series. These journeys invite you to slow down, quiet your thoughts, and drift into rest while exploring the wonders of the universe. If you enjoy these moments of calm discovery, support us by subscribing to this channel and visiting thingsofthestars.com. Tonight, we turn our attention to the force that holds us here, keeping our feet gently pressed to the ground, anchoring the atoms within us, and shaping the entire visible universe. We speak of gravity. If you are comfortable now, allow your shoulders to drop and feel the simple, steady weight of your own body resting against the surface beneath you. This weight, this simple insistence on remaining connected to the earth, is the constant, silent signature of gravity. Take a breath. The universe is patient. We are suspended on a spinning sphere, moving swiftly through the void, yet we feel safe, still, and grounded, thanks entirely to this remarkable interaction. The feeling is so intuitive that our brains are evolutionarily equipped to grasp its effects immediately here on Earth. Yet, this phenomenon, which feels so strong and reliable, harbors secrets that baffle the brightest minds in physics, operating in ways that defy our conventional expectations. For centuries, thinkers have wrestled with this invisible pull, seeking to understand why an apple falls or why a flame rises. From early philosophical definitions that saw down as a natural striving toward the center of the cosmos to the grand, sweeping equations of modern relativity, the story of gravity is the story of human inquiry itself. Tonight, as we settle into the deepening quiet, we will explore this history, tracing the path from simple observation to the mind-bending theories that describe the curving fabric of reality. We will drift through the paradoxical nature of gravity, seeing how it manages to be both the weakest of all fundamental interactions and, simultaneously, the undisputed architect of cosmic structure. We will ponder its influence on time itself, examining how mass affects the flow of moments, making your clock tick slightly differently depending on your altitude. And finally, we will approach the edge of our current knowledge, peering into the great modern mystery, how to reconcile this smooth, continuous geometric description of gravity with the chunky, discrete world of quantum particles. Allow these scientific reflections to become a gentle rhythm, weaving relaxation and intellectual curiosity into a single, seamless moment. You are grounded, safe, and connected to everything. Feel the steady assurance of the ground beneath you, that grounding force, that pull toward the center of the earth, is a gravitational interaction. Every planet, including our own, is surrounded by a gravitational field. In the Newtonian view, which we will discuss shortly, this field exerts an attractive force on all objects. For most applications, this familiar classical model works perfectly well, describing the motion of objects toward a body in proportion to the product of their masses. Yet, here is where the great paradox begins. The Earth is a truly immense gravitational source. Its mass registers at 597 septillion kilograms, a number followed by 24 zeros. This enormous accumulation of matter generates a gravitational pull powerful enough to keep our moon tethered in orbit and strong enough for the moon in turn to drag the entire ocean in its wake, creating the steady rhythm of the lunar tides. Gravity is the primary driver for the large-scale structures we see in the universe, initiating the coalescence of primordial hydrogen and dark matter into the stars and galaxies that define the cosmos. And yet, this force, the sculptor of galaxies, is almost inconceivably weak. Consider how effortlessly you overcome it every time you stand up or lift a book. You are, in that small act, winning a localized tug of war against the entire planet. To truly appreciate this weakness, we must compare gravity to the other fundamental interactions that govern physics. These are the strong nuclear force, the weak nuclear force, and electromagnetism. The strong nuclear force is the strongest of them all, binding protons and neutrons together within the nucleus of an atom, overcoming the natural electrical repulsion between the positively charged protons. It is a massive force, yet its range is limited solely to the subatomic scale, confined within the nucleus. Compared to this titan of interaction, gravity is weaker by a factor of about 100 million trillion times. Next comes the weak nuclear force, responsible for processes like radioactive decay and playing a crucial part in nuclear fusion and fission. Even this force, which carries the word weak in its name, is still stronger than gravity by a factor of 10 to the 25th power. Like the strong force, the weak force operates only on subatomic scales, having a finite, limited range. Finally, we have electromagnetism, the force we are perhaps most tangibly familiar with in daily life, rooted in the properties of charged particles like electrons and mediated by photons. It is electromagnetism that gives rise to modern wonders like electricity and governs the atomic bonds within our own cells. Although weaker than the strong nuclear force, electromagnetism is still stronger than gravity by a massive factor. A simple, calming demonstration of this dramatic difference is seen in the humble static charge. The small electromagnetic repulsion generated by just a few electrons transferred onto a person's hair can easily compensate for and overcome the entire gravitational attraction exerted by the mass of the Earth. The reason why gravity, despite being the weakest interaction, becomes the dominant force in the universe is tied to its persistence and its reach. Gravity has an infinite range, meaning that every object possessing mass exerts a gravitational effect on every other object with mass across the known universe. While the other forces may switch off or cancel each other out over large distances, gravity's effect is unceasing. However, even though its reach is technically boundless, its influence diminishes exponentially with distance. It operates based on an inverse square law, meaning the gravitational pull weakens in proportion to the square of the distance between the objects. If you double the distance from a massive body, the gravitational strength drops off by a factor of 4. Applied across the vast distances of the cosmos, the force eventually becomes so minuscule as to be negligible, though it never truly reaches zero. This universal yet rapidly diminishing influence is why gravity, over unimaginably long periods of time, was able to transform a featureless void into the intricate structure of stars, planets, and galaxies we see today. Now, let us settle deeper into the quiet and drift back through the ages, tracing how humanity first began to define this mysterious connection to the ground. For nearly 2,000 years, the understanding of gravity was rooted in the philosophy of the ancient world, particularly that of Aristotle in Greece. Aristotle believed that objects fell toward the earth not because of a universal force, but because the earth was the fixed, central point of the universe. The heaviest elements, earth and water, had a natural tendency, a quality he termed their nature or gravity, to seek this center. Light elements like fire and air naturally rose toward the celestial realm. Gravity, therefore, was a characteristic of the element itself, driving motion in a straight line toward a specific location. This view, though widely accepted, was not universal. In ancient Indian cosmologies, particularly among mathematician astronomers, a strikingly modern insight emerged centuries before the scientific revolution in Europe. In 6028 AD, the Indian scholar Brahmagupta proposed that gravity was an attractive force that inherently draws objects to the earth, using the term Gurudvakarao to describe it. Other thinkers in the ancient Middle East, such as the Persian intellectual al-Biruni, correctly assumed that other heavenly bodies must also exert a gravitational attraction, suggesting the force was not unique to the Earth. The next great leap came during the scientific revolution in Europe, spurred on by thinkers like Galileo Galilei. Galileo is famous for the likely legendary experiment at the Leaning Tower of Pisa, where objects of different weights were dropped to demonstrate that they fall at the same rate. But his true contribution came from meticulous experiments using balls rolling down inclines. He understood that air resistance was the reason why low-density objects with high surface areas, like a feather, appeared to fall slower in an atmosphere. This idea, that gravity acts universally on everything in the same way, is called the equivalence principle. Imagine, for a moment, being an astronaut on the moon, where there is no atmosphere to slow down objects. During the Apollo mission, astronaut David Scott performed a dramatic demonstration. He dropped a hammer and a feather simultaneously, as Galileo predicted centuries earlier, and as the equivalence principle requires, they struck the lunar surface at exactly the same moment. Every particle, every molecule, and every cell experiences gravity in precisely the same universal way. Galileo's insights on motion were crucial. He developed the concepts of the reference frame and the principle of relativity, observing that the laws of physics appear identical on a moving ship as they do on land. These ideas laid the essential foundation for Sir Isaac Newton. Newton synthesized these threads into the grand realization that the same force causing an object to accelerate toward the earth, like an apple falling in his famous anecdote, was also responsible for keeping the moon in its orbit and the planets revolving around the sun. Newton's law of universal gravitation, published in 1687, unified celestial and terrestrial mechanics for the first time. Gravity was declared a universal force, operating on objects in proportion to the quantity of matter they contained and propagating outwards to immense distances. Newton formulated the law as the gravitational force being proportional to the product of the two masses involved and inversely proportional to the square of the distance between them. This inverse square relationship explained Kepler's empirical observations that planets orbit the Sun in ellipses. This quantitative, predictive power of Newton's law was profoundly successful. For example, in the 1840s, irregularities observed in the orbit of Uranus led astronomers to predict that an unknown massive object must be pulling on it. Using Newton's equations, astronomers were able to calculate where this unseen body should be. However, Newton's triumph came with a philosophical difficulty. His description of gravity required a force that acted instantaneously across vast distances, a concept he termed action at a distance. Newton confessed he did not know why gravity worked, only that his equations accurately described how it worked. He famously stated, "Hypotheses non fingo," or "I frame no hypotheses non fingo," or "I frame no hypotheses regarding the mechanism of the force." Take a breath. Allow the quiet mystery of the universe to settle around you. The conundrum of action at a distance persisted for over 2 centuries until the early 20th century, when a subtle observation brought Newton's model to its knees. Astronomers had noticed a slight, unexplained eccentricity in the orbit of Mercury. The point of Mercury's closest approach to the Sun, its perihelion, was advancing by a tiny amount, about 43 arcseconds per century, more than Newton's laws, even accounting for the pull of all other known planets, could explain. The search for a hypothetical inner planet that might explain this anomaly proved fruitless. The answer required Albert Einstein to revolutionize our very understanding of space and time. Einstein had already developed the special theory of relativity, which showed that the speed of light is fixed and absolute, independent of the observer's motion. This idea clashed fundamentally with Newton's concept of instantaneous action at a distance, implying that gravity itself must have a speed limit. Einstein's breakthrough, general relativity, began with the refinement of Galileo's equivalence principle. Einstein realized that the equivalence of inertial mass, the resistance of an object to acceleration, and gravitational mass, the mass that generates and responds to gravity, meant that in free fall, an accelerated coordinate system exists where there is no local gravitational field. This was his happiest thought. Imagine the feeling of being in free fall, a skydiver before the parachute opens, or an astronaut orbiting the Earth. You feel weightless, or 0G, even though Earth's gravity is clearly acting on you. Every cell, every particle in your body is accelerating at the same rate, so nothing is pushed or torn apart. You cannot feel gravity when you are free falling. This led Einstein to realize that being in a gravitational field is locally indistinguishable from accelerating in empty space. If gravity can be made to locally disappear simply by falling, then perhaps gravity isn't a force at all. Einstein reconceived gravity not as a force, but as a manifestation of the curvature of space-time itself, a unified four-dimensional framework that combines the three dimensions of space with the dimension of time. Mass and energy, according to Einstein, tells space-time how to curve, and the curvature of space-time tells objects how to move. When a massive object, like the sun, is placed upon it, it creates a dimple or warp. Planets do not orbit the sun because an invisible force pulls them. They orbit because they are following the straightest possible path, called a geodesic, through the curved region of spacetime created by the sun. This path, while appearing as a curved ellipse in three-dimensional space, this is a profound conceptual shift. Gravity is the geometry of reality. Einstein's general relativity was immediately successful. It naturally accounted for the 43 arcsecond per century discrepancy in Mercury's orbit simply as an effect of the space-time curvature near the Sun. Furthermore, it made entirely new, counterintuitive predictions that differed from Newton's theory. One such prediction was the influence of gravity on light. Light, which has no mass, was previously thought to be unaffected by gravity in the Newtonian sense, other than a small theoretical deflection if treated as a particle. Einstein's theory, however, implied that light must follow the curvature of space-time. In 1919, during a total solar eclipse, astrophysicist Arthur Eddington led an expedition to test this. By measuring the apparent positions of distant stars whose light passed close to the eclipsed sun, Eddington confirmed that the starlight was bent by the sun's gravitational field. Crucially, the degree of bending matched Einstein's prediction, which was twice the amount predicted by Newtonian calculations. This experiment catapulted Einstein to worldwide fame and solidified the acceptance of general relativity in the scientific community. Drifting deeper now, we explore the spectacular, time-bending consequences of a curved space-time. One of the most remarkable phenomena predicted by general relativity is gravitational time dilation. This is the idea that time runs more slowly in the presence of a strong gravitational field. Think about this deeply. We tend to assume time is a universal, steady flow. But in reality, we are all experiencing slightly different rates of time depending on our altitude and velocity. Since gravity weakens with increased distance from a central mass, time dilation diminishes as you move farther away and time appears to pass more quickly. A person standing on a mountain peak farther from the Earth's center of mass will experience time slightly faster than someone at sea level. Though this difference is inconsequential for human experience, a clock just 1 kilometer away from the Earth's center will record a 24-hour period as being roughly 10 nanoseconds longer than one on the surface. The accumulated difference over vast stretches of time is astonishing. For instance, the Earth's core is estimated to be about 2.5 years younger than its surface, accumulating that tiny difference over the 4.5 billion years of the planet's existence. This difference is far from theoretical. It has a very real impact on technology we use every day, such as GPS satellites. GPS satellites orbit at an average altitude of about 20,000 kilometers. Because they are further from Earth's mass, they experience weaker gravity, leading to gravitational time dilation. However, they are also moving at around 22,000 kilometers per hour, which introduces an opposing time dilation effect due to velocity as described by special relativity. When both relativistic effects are factored in, the GPS satellite clock gains approximately 38 microseconds per day relative to a clock on Earth's surface. If these satellites lacked sophisticated, built-in error correction systems to account for this tiny time difference, the navigational calculations would quickly become useless, resulting in miscalculations of location off by kilometers. This daily correction is a powerful, quiet testament to the accuracy of Einstein's theory. Gravity also influences light in another incredible way, beyond simple deflection. When an enormous concentration of mass, such as a large galaxy, lies between us and a distant light source, the massive object warps the space-time around it. This curvature acts like a massive cosmic magnifying glass or a lens, bending the light from the background object toward the observer. This phenomenon is known as gravitational lensing. This happens even though light has no mass, simply because it must follow the contours of the curved space-time. As massive objects move and accelerate violently through space, they create ripples in the fabric of space-time, much like throwing a stone into a still pond. These ripples are known as gravitational waves, and general relativity predicted that energy could be transported out of the system in this form. The first indirect evidence for these waves came in 1973 through observations of a binary pulsar system, a pair of neutron stars orbiting each other. Scientists observed that this system was slowly losing energy at a rate precisely consistent with the predicted loss due to gravitational radiation, causing the orbital period to decrease. A century after Einstein first predicted their existence, gravitational waves were directly detected for the first time. On September 14, 2015, the LIGO detectors measured faint gravitational waves emanating from the collision and merger of two massive black holes that had occurred 1.3 billion light years away. This direct detection was hailed as a monumental scientific achievement, confirming the theory in spectacular fashion and opening a new window into the universe. Gravitational waves provide us with clues to the most extreme manifestation of gravity, the black hole. A black hole forms when an extremely large mass is confined to an incredibly small region of space, creating such an intense gravitational field that space-time curves back upon itself. This leads to an inescapable well of curved space-time. Once anything, including light, passes a certain boundary known as the event horizon, it cannot escape the gravitational pull. The gravity is so strong that even if you could travel at the speed of light, you would still be pulled inexorably toward the center. As an object, or perhaps a theoretical physicist, approaches the black hole, the curvature of space-time increases dramatically. Inside the black hole, the classical notions of space and time even switch, making the distance to the center feel more like a time scale, an inevitable point in one's future. Black holes are not merely theoretical. The discovery of Cygnus X1 in 1971 confirmed the existence of these objects, which emit X-rays as they consume nearby stars. Furthermore, scientists have found proof that every large galaxy contains a supermassive black hole at its center, with masses equivalent to millions of suns. The one at the center of our Milky Way is called Sagittarius A, possessing a mass about 4 million times that of the Sun. These extreme gravity zones, confirmed by observation, demonstrate that general relativity works with impeccable precision, even at high curvature scales. Yet, this very success leads us to the final great puzzles of the cosmos. We now arrive at the frontiers of discovery, the places where gravity reveals its deepest secrets and greatest contradictions. Allow your mind to drift across the largest scales of the universe, moving beyond galaxies and local clusters, spanning billions upon billions of kilometers. When we look at the cosmos on these truly immense scales, gravity is a dominant player, but it reveals its incompleteness through two great mysteries. First, we encounter dark matter. Observations of spiral galaxies show that stars on the outskirts are moving faster than they should, based on the observed distribution of luminous visible matter. This suggests that there is far more mass present than we can see. We know that it interacts through gravity, forming clumps called dark matter halos that attract hydrogen gas, leading to the formation of stars and galaxies. However, it does not interact through the electromagnetic force, meaning we cannot detect it using light, and its fundamental nature remains an unsolved problem in physics. Second, and perhaps even more perplexing, is dark energy. Based on gravity's constant attractive pull, we might expect the expansion of the universe, which began with the Big Bang, to be slowing down. But when astronomers look at the larger scales, the opposite is true. The expansion of the universe seems to be accelerating. One of the theories attempting to account for this acceleration relates back to the nature of empty space itself. Even the best vacuum, a cosmic void far from any galaxy, is never truly empty. It is filled with quantum fluctuations from all known particles, a pervasive vacuum bath. This vacuum energy, which fills the entirety of space uniformly and has done so since the beginning of time, doesn't just curve space-time locally like a planet does. Instead, it pushes the boundaries of space-time outward in every direction. This outward push, this inherent energy of the vacuum, should lead to an accelerated expansion. The challenge is that when physicists try to calculate the expected rate of this acceleration based on the known vacuum energy, the discrepancy with what we observe is enormous, about 28 orders of magnitude too large. This is often called the biggest discrepancy or embarrassment in the history of science, as it pits two impeccably precise pillars of modern physics, general relativity and the standard model of particle physics, against one another. This points us to the final, deepest puzzle of gravity, the failure to reconcile it with the laws of the very small, quantum mechanics. Quantum mechanics describes the subatomic realm. It successfully describes the other three fundamental forces, electromagnetism, weak and strong, using a framework where interactions arise from the exchange of discrete quantized particles. For example, the electromagnetic force is mediated by the exchange of photons. However, general relativity describes gravity on large scales as a smooth, continuous distortion of space-time. When physicists try to zoom in and quantize gravity, incorporating it into the quantum mechanical framework, the mathematical models fail spectacularly at extremely small distances, specifically at the Planck length. It seems at these points the theory tells us nonsense, such as predicting greater than 100% probability of an event. If gravity were a quantum force like the others, there should be a corresponding force carrying particle. This hypothetical particle is called the graviton. In theory, masses would exchange virtual gravitons to produce the attractive force. Although this concept reproduces general relativity in the classical limit, the graviton remains strictly hypothetical, having never been observed. Furthermore, unlike the other forces which cannot be made to disappear, gravity can be eliminated in a free-falling frame, which complicates the notion of it having a mediating particle. The search for a theory that unites general relativity and quantum mechanics, a quantum gravity theory, or a theory of everything, is the paramount quest in modern physics. Two leading candidates have emerged to attempt this unification. String theory posits that the fundamental constituents of nature are not point particles, but tiny, vibrating strings. Remarkably, string theory naturally includes a massless particle that behaves exactly like a graviton, suggesting gravity is a built-in feature of the string's vibrations. The other major approach is loop quantum gravity, which seeks to quantize space-time itself. It envisions space not as a smooth continuum, but as a network of discrete atomic-like loops, giving space a fundamental structure at the Planck scale. Both theories, along with many innovative proposals, face the hurdle of experimental verification. Some physicists now propose that perhaps gravity is not meant to be integrated into the existing quantum framework at all, and that an entirely new model of physics, one that seamlessly combines the grand classical scale with the quantum scale, is required to fully understand reality. The universe ultimately does not have to be simple, but the human intellect persists in its desire to understand the fundamental nature of the cosmos. And so, we conclude our journey through the deepest currents of gravity, bringing our focus back from the far reaches of merging black holes and accelerating cosmic expansion to the quiet comfort of this moment. You are here, still and resting. The feeling of being grounded, of having gravitas, is an echo of this fundamental phenomenon. It is the force that connects us to the history of the earth, keeping us steady even as the world spins. Gravity's story is a continuous evolution. It began in antiquity as a quality of heavy elements seeking their natural place. It transitioned in the age of Newton to a precise, universal law governing a clockwork universe. This elegant framework, general relativity, has been superbly tested in every domain, from the movements of satellites to the extreme environments around black holes. Yet, gravity remains the most mysterious of the fundamental interactions. It is the weakest force, yet the architect of everything large. It is a smooth, geometric curve, yet it must somehow interact with the chunky quantum world. Think of the graviton, the shyest, most subtle particle hypothesized by physics. We may never detect a single one because we interact with gravity so weakly. But the quiet persistence of these unobserved messengers, working in cohesion across billions of years, dictates the fate of galaxies, the formation of stars, and the shape of our home. You are held in place by this grand cosmic geometry. Your weight is a local reflection of the sun's warpage, the earth's mass, and the motion of all things in the universe. As you prepare to sleep, know that you are traveling along a perfectly straight path, a geodesic through the curved space-time continuum. It is the universe itself that is curved around you, creating the sense of pull and stability. Take a breath deeply and slowly. Allow your thoughts to release their own internal gravity, settling into the quiet stillness of the night. Sleep now under the influence of this persistent, gentle, and deeply profound interaction. You are connected to the stars, to the fabric of reality, and to the quiet peace of the universe.